Hello everyone, in this video we'll be picking up where we left off in section 8.4 with example 3. So we can extend the use of trig substitution to cover integrals involving expressions that look like n over 2 in the power. Why? Because remember, anytime we write n over 2 in the power, whatever's in the denominator becomes the root, right? And so since it's 2, it's the square root, so I can always have the square root to the nth power. And since I have the square root to the nth power, I can still use these substitutions, right? So here what we're going to do is we're going to realize that we get x squared plus 1, which is going to look like u squared plus a squared, so that our u is equal to what's being squared, x, our a is equal to 1, and we can use the substitution tangent. Right? So here I get, and we'll proceed as usual, and you'll see where the 3/2 power comes into play, and it comes into play in the substitution part, right? So this integral looks like, we can go ahead and rewrite it so you can see what I mean. This looks like 3/2 dx. Well, this is really 1 over the square root of x squared plus 1 cubed, right, dx. So if we figure out what these pieces are, what the square root is, which we're going to do by the trig, what dx is, which we're going to do by the trig, we can still do a substitution, right? So again, our substitution here is, it should be, remember this is u equals a tangent of theta, right? So what's our u in this case? Our u is x, and then a is going to be 1, so x equals tangent of theta. All right, so we need the derivative to get dx, so the derivative of tangent is secant squared theta, and then we chain on that d theta. So that is something we're going to be substituting. And again, what else do we need? We need the square root of x squared plus 1, right? So what did we replace x with? We replaced x with tangent. So tangent squared plus 1 underneath the square root. So then I get tangent squared theta plus 1 underneath the square root. Tangent squared theta plus 1 is secant squared. So again, I get that, continuing this equal sign, x squared plus 1 is secant theta. And that's all I need for the substitution, right? So now I'm going to substitute. So I get the integral of our original guy was, we rewrote it to be the square root of x squared plus 1 cubed underneath, or in the denominator. So this looks like, well, what did we replace x squared plus 1 with? We replaced it with secant. So this looks like secant theta cubed. And then what would we say dx was? Dx was just secant theta. So this is secant theta d theta. So we end up getting, right, 1 over secant squared theta. Or I'm sorry, this should be secant squared right up here. Try that again. When I did the substitution, right here, we knew that dx was secant squared, right? So this should have been secant squared theta d theta. So then when I did this canceling, I should get this. So it should just be 1 over secant in the denominator, d theta. What's 1 over secant? Secant, remember, that's the flip over of cosine. So this is just like cosine of theta d theta, which is positive sine theta plus c. But again, remember, we're not done because this is in terms of theta, right? So I need to replace that. So here's where we do our side work with our right triangle trig. So we have x equals to tangent theta, right? So x equals tangent theta. So this means that x over 1 is equal to tangent theta. Remember, so that I said that's the trick when there's nothing to divide there. So remember, this is op over adjacent. So our triangle here looks like theta. Opposite is going to be x, adjacent is going to be 1, so this is going to be the square root of x squared plus 1. Again, if I breeze through that too fast, how I got that x squared plus 1 to be the hypotenuse, just do the Pythagorean theorem, right, with x and 1. So what do we need? We need sine theta. Sine theta, remember, is opposite over the hypotenuse. So what's our opposite? Our opposite is x. Our hypotenuse is the square root of x squared plus 1. So again, that's our last substitution. So I get this is sine of x over the square root of x squared plus 1. No, sorry, not sine of. That is what sine is, right? So made a mistake there. That's not what theta is. That's what sine of theta is. So that whole thing becomes x over the square root of x squared plus 1 plus c. And that is our final answer. Okay, so now what happens if we have a definite integral? Well, a lot of times in these examples that I've been doing with the definite integral, I find the antiderivative completely, and then I put the original limits in, and we roll with it that way. The other way to do u substitution with the definite integral is to find new limits that have to do with your u substitution, so that way you don't have to resubstitute back in. And that's often what's going to be best for this limits, in these trig substitution problems. So I'll show you what I mean here. Okay, so in this example, I can't remember what our last color was. I think it was green. This is going to be one of the u squared minus a squared examples, right? So this one's going to be a secant substitution. All right, so this one looks like it's x squared minus 3, and that's going to be equal to the square root of u squared minus a squared, right? That's going to be a u substitution. Again, we have to be kind of careful here. Our u is what's being squared, so that's x. Now our a, what do we square to get 3? Right? Because remember, we can't just put 3 here, but we square radical 3 to get a, right? So anytime it's not a perfect square that you're subtracting or adding, you have to do the radical part, right? So our substitution in this case is that u, oops, I should write it up here. Our substitution is u equals a secant theta, right? So our u is x, our a is radical 3, and we get secant theta. So I'm going to do everything the same that we did before, where I find what x is, so I need to find x squared minus 3 underneath the square root, and I need to find dx. And then the last thing I'm going to do is I'm going to use this substitution here in order to find my limits also in terms of theta. Right now, the limit 2 and radical 3 are in terms of x, so we need to get those in terms of theta as well, but we'll do that at the end. Okay, so we need dx. So dx is the derivative, so radical 3 hangs out for the ride. The derivative of secant theta is secant theta tangent theta, chain on the d theta, right? And so, like I said, now we're going to do the upper and lower limits. So change from x limits to theta limits, right? So if, we'll do the lower limit first. If x equals to radical 3, then we're going to use, again, we're going to do that by our x equals radical 3 secant theta in order to change it. So x equals to radical 3, then what do I get? Well, x is equal to radical 3, and then radical 3 secant of theta, right? I'm using this equation right there. And I'm plugging in x equals both those values, and I'm finding theta, right? So if I divide by radical 3, I get 1 is equal to secant theta. Here's where I like to rewrite cosines and sines because I'm more familiar with it, right? So this is 1 over 1, so if I flip it over, it's still just going to be 1 over 1, and flipping over secant is going to be cosine theta, right? Because remember, secant theta is 1 over cosine theta, and if I were going to solve that, I get the same equation. So now I can do cosine inverse of 1 is equal to theta. Where does cosine equal to 1? Cosine equals to 1 at 0. Right? So I get theta equals to 0. is my lower limit. So now my upper limit, if x is equal to 2, what do I get? I get 2 is equal to the square root of 3 secant theta. So I get 2 over radical 3 is equal to secant theta. Okay, so 2 over radical 3 is equal to secant, but secant is 1 over cosine theta. Again, I convert it to cosine just because I'm more familiar with it. So now I can flip them both over, right? So this means radical 3 over 2 is equal to cosine theta. Right? If I flip them both over, that's a legal move. So now I know cosine inverse of radical 3 over 2 is equal to theta. When does cosine equal to radical 3 over 2? Well, that's at theta equals to pi over 6. So that's my my upper limit. So now I have everything that I want. Right? I have my two substitutions for my trig, and I have my limits. So let's rewrite the problem here. So now, I guess I was just writing substitute. And in this case, since it's a limit problem, or I'm sorry, not a limit problem, a definite integral problem, I won't have to do the resubstituting back in with the right triangle trig. Right? This whole thing was getting rid of the right triangle trig. Okay, so my original integral looked like the square root of 3 to 2, and then, I forgot to do my x squared, right? I needed to find this, and I never did I? So we should do that right here, right? Square root of x squared minus 3, right? I need to know what that is in order to do my substitution. So what did we say x was? X was radical 3 secant theta squared minus 3 underneath the square root. So I get 3 secant squared theta minus 3 underneath the square root. Pull out a 3, I'm left with secant squared theta minus 1 underneath the square root. The square root of 3 is just square root of 3. And then secant squared minus 1 is tangent squared theta. So I get radical 3 tangent theta. That's what x squared minus 3 is. So I apologize. I should have done that at the beginning, but I didn't. And again, that's what we expected, because if you go back up here to our original thing, we said that I should get whatever a is tangent of theta for my substitution, and that's exactly what I got here. Oops. Okay, so now I can substitute. So again, let's write the original problem. Square root of x squared minus 3 over x dx. So first we can substitute our limits, right? Our limits we said were 0 and pi over 6. Now instead of the square root of x squared minus 3, I get radical 3 tangent theta. Instead of x, what was x? That was radical 3 secant theta. And then instead of dx, I got radical 3 secant x tangent, secant theta tangent theta. So this is radical 3 secant theta tangent theta d theta. So now I end up getting the integral from 0 to pi over 6, secant, radical 3, so I get radical 3 out front. Tangent squared theta d theta. And now this is a trig integral, right? But actually this is a pretty simple one. Anytime I had even powers of tangent with no secants, I should convert it to secant, right? So this one's pretty simple. Here, if I have tangent squared, I replace that with, because we don't know what tangent squared theta is. I don't know how to take that integral. But I do know that I can replace that with secant squared theta minus 1, which is convenient because now I know how to take the antiderivative of secant squared, right? The antiderivative of secant squared, what function has secant squared as its derivative? Tangent, right? So that's one we know how to do. So now I get radical 3 The antiderivative of secant squared, like I said, was tangent theta, and then minus the antiderivative of 1 is theta. And now, since my limits are in terms of theta, life is good, and I can just plug those in. So I get radical 3, tangent at pi over 6. Tangent at pi over 6 is going to be 1/2 divided by radical 3 over 2. So in other words, multiply by 2 over radical 3, right? Because at pi over 6, I get 1/2 radical 3 over 2. Right? This is pi over 6. So when I do tangent, I flip them. I have to divide 1/2 by 2, radical 3 over 2, which is the same as multiplying, and then theta, which is just pi over 6. Now subtract tangent at 0. What 0, remember, what are my values? They are the x value 1, the y value 0. So this would just be 0 over 1, which is 0, minus 0 is what I was plugging in. Right, so this all nets to 0. And then I end up getting radical 2 cancels out, radical 3 cancels out. So I get 1 minus radical 3 pi over 6. Right, because remember, I distribute that radical 3 to both terms there. So when I distribute to the first term, everything cancels out, and I get the 1. When I distribute to the second term, I get that, which is approximately negative 0.0931. Right? Just because it's a negative number doesn't mean we did anything wrong. That just means there's area underneath the x-axis. Right? Okay. So again, when using trig substitution to evaluate definite integrals, you must be careful to check that the values of theta lie in the interval discussed at the beginning of the section, which I actually kind of forgot to discuss here. In this case, I should have mentioned in the secant case here, this we have to be a little bit careful with. So here I get that I got to be careful. This was fine, but it was only fine for certain values. So the square root of u squared minus a squared is equal to a tangent of theta for when u is bigger than a and when our theta is between 0 and pi over 2, and it's negative a tangent theta for when u is less than negative a and when we have these bounds, when theta is between 2 and pi over 2 and pi. So I shouldn't have written this. I should have written this right here, because we have to be careful. When I take that square root, just like I did, I would get a negative sign in some of those cases when I take that square root of tangent, right? But in this case, our values were fine because pi over 6 lies in this interval, right? So I could use the positive 1, right? But if pi over 6, if 0 and pi over 6 weren't in that interval, I would have had to be more careful and use the negative. Okay, so trig substitution can be used completing the square. Again, I posted a video on completing the square because it's something that you learned way back when, probably in college algebra. But it is a trick that we used oftentimes, so I will kind of go through it in this example. So remember, we can use trig substitution when it looks like something squared minus something else squared underneath the square root, right? In this case, that's not what we have here. We have a 4x and then an x squared. So that 4x is not what we want. So we're going to complete the square to get what we want, right? To make it something squared minus something squared. Okay, so we get 4x minus x squared, right? I don't like that. I want it to look like something squared minus something squared. The first thing I need to do is factor out a negative. So I get if I factor out well, actually, first thing I'll do is I'll switch the order of everything. So minus x squared plus 4x. I just wrote the order around, so the x squared came first. Now I'm going to factor out a negative sign, because in order to complete the square, I need to have the coefficient of x squared be positive 1 right here, not negative 1. So now how does complete the square work? I look at the center term, which is negative 4, and I take 1/2 of that, and then I square it. Right? What's 1/2 of negative 4? Negative 2. Square it, I get positive 4. Right? So I do this. I go x squared minus negative 4x, and then I add 4, and I subtract 4. So maybe I'll do it a different color here. So I'm going to add 4 and also subtract 4, because that means I'm really doing nothing. Right? Now I need to get rid of this guy, because this piece right here is x minus 2 quantity squared. And that's why I completed the square, because I know that I can make that a binomial squared. But I got to get rid of that minus 4. So in order to do that, I'm going to distribute this negative sign to the minus 4 and get it out of there. Right? So this looks like minus x squared minus 4x plus 4. And then if I did minus negative 4, I would get a plus 4 on the outside. The negative sign here is a little bit pesky. So then now, like I said, this I can factor. This factors as x minus 2 squared, right? If you don't believe me, square it out, but it's always going to be the middle term divided by 2 is what I'm subtracting there, or what my other term of my binomial is, and then plus 4. And again, I'm going to rearrange this so it looks like 4 minus x minus 2 quantity squared, and that's what 4x minus x squared is, right? And so that's what I'm going to kind of substitute here. And this one is going to be, it's u squared, or actually, sorry, something minus u squared. So this one's going to be a sine. So sine, I believe we did with purple, right? And if you don't believe me, multiply this out and you'll see that it's exactly equal to 4x minus x squared, right? Okay. Again, why is this helpful? So now we've rewritten our problem as 4x minus x squared underneath the square root over top, or underneath x dx. So I've rewritten this as 4 minus x minus 2 squared underneath the square root x dx. So now I can have one of our trig substitutions, right? 4 minus x minus 2 squared is equal to, I guess I was doing this in purple. So here I get 4 minus x minus 2 squared underneath the square root is equal to a squared minus u squared, right? So in this case, our a is equal to 2, our u is equal to x minus 2, and we're going to use the substitution u equals a sine theta, because it's something squared minus the variable squared, right? So what is u? U is x minus 2, and then that's going to be a sine theta. A is 2, so 2 sine theta, right? So what does that mean? That means x is equal to 2 sine theta plus 2, right? And that's one of the things we're going to need to substitute, because that's what we've got here. So now we need to figure out what, we've got x, we need to figure out dx, and we need to figure out the square root of 4x minus x squared. So dx is the derivative, so it's 2 cosine theta, right? And then the derivative of 2 is, the derivative of 2 is 0. And then now we got the square root of 4x minus x squared. Well, again, we said that by completing the square was equal to 4 minus x minus 2 squared. So 4 minus, what did we say x minus 2 was? X minus 2 we replaced with 2 sine x, or 2 sine theta, sorry, squared, right? So this is 4 minus 4 sine squared theta. So I get 4 factored out, 1 minus sine squared theta. Square root of 4 is 2. 1 minus sine squared theta is cosine squared theta. So I get 2 cosine theta is equal to my 4x minus x squared. Right? And now I have everything to substitute. Right? So now I can substitute. So I get the original integral was x over 4x minus x squared dx. Well, x we know is 2 sine theta plus 2. The 4x minus x squared in the square root is 2 cosine theta. And then our d theta is 2 cosine theta d theta. Sorry, our dx is 2 cosine theta d theta. So I end up getting here 2 cosine thetas cancel out. I can factor out a 2 and be left with sine theta plus 1 d theta. All right, if I factored out a 2 in the numerator. And what do you know? We know how to take the antiderivatives of these, right? So what's the antiderivative of sine? Well, that's negative cosine theta, and then plus theta, and then plus c. All right, so negative 2 cosine theta plus 2 theta plus c. But now we need to find our theta, our cosine of theta and just theta. So here's where we do some side work. We're going to put the side work right here. All right, so what do we know? We know that x over 2 is equal to 2 sine theta. Sorry, x minus 2 is equal to 2 sine theta. So that means that x minus 2 over 2 is equal to sine theta. First and foremost, we need to know what theta is. If I want to find theta, I can take the sine inverse of both sides, right? Sine inverse of x over x minus 2 over 2 gives me theta, right? So anytime you need to find just theta, which happens sometimes, we haven't had that in any cases so far, you just need to take the inverse of whatever your substitution was, just like I did there. Now, what's the other thing I need? I need cosine of theta. So I actually don't even need to do any more side work because I know that 2 cosine of theta is equal to the square root of 4x minus x squared by my substitution. So what does that mean? That means that cosine of theta is equal to the square root of 4x minus x squared over 2. Right? And if you don't believe me, you could again do right triangle trig and determine those exact same values. But if you don't have to use it, why not just use what you already have, right? So minus 2, what did we say cosine was? It was the square root of 4x minus x squared over 2 plus 2. What did we say theta was? Theta was sine inverse of x minus 2 over 2 and then plus c. So here I get minus the square root of 4x minus x squared plus 2 sine inverse of x minus 2 over 2 plus c. All right? So again, this problem, it didn't look like we were going to be able to do a u substitution for trig, but we were able to complete the square here and then make it look like a sine substitution problem. Right? Okay, special integration formulas. So we've done all this work for trig substitutions, but if you were to do them over and over again, here's the formulas you would get. So if I ask you on an exam or on a quiz to do a trig substitution problem, you must do all the steps we did earlier, right? But for example, if I have like an application of it, like this arc length problem, you could use one of these formulas so you don't have to do all that work for a trig substitution. Right? So for this example here, we want to find the arc length of the graph of f of x equals 1/2 x squared from x equals to 0 to x equal to 1. Remember, in general, arc length is the integral from a to b, 1 plus the derivative squared underneath the square root dx. right? So we need to find our derivative. The derivative of 1/2 x squared is just x, and it gives us that it goes from 0 to 1, right? Because we want to find the arc length from 0 to 1. So I get 1 plus, and then it's the derivative squared. The derivative is x, so this is 1 plus x squared underneath the square root dx. So again, you should do, if I was being hateful, I'd say, okay, I need you to do the trig substitution, right? In this case, my a is equal to 1, my u is equal to x, and then I would need u equals a tangent theta to be my substitution, right? But again, we have these formulas here, so now I can use formula 3, right? So let's use formula number 3. In this case, what is our u and what is our a? Again, our u is the one with x, so that's, what are we squaring? We're squaring x, and so I don't know why I put a comma there. So this is with u equals to x and a equals to 1, right? So s is equal to, and remember this is in general for an antiderivative, but in our case we're going to be using the definite integral, right? So I do 1/2 u, which u is x, so 1/2 times, put a bracket here, x, now the square root of x squared plus 1, plus, what is a? A is 1, so 1 squared ln of u, which is x, plus the square root of x squared plus 1. Notice the square root of x squared plus 1 is the same as the square root of 1 plus x squared, right? And then I'm going to evaluate that, instead of the plus c, I'm going to evaluate that from 0 to 1, right? So here I get 1/2, and now for 1, I get 1 times 1 squared plus 1, so this is radical 2, plus ln of 1 plus, and then again radical 2, and then subtract. Now I plug in 0, so the first term goes away. If I plug in a 0 there, the second term is ln of 0 plus the square root of 1, so ln of 1, right? So here I end up getting ln of 1 is 0. So here I end up getting 1/2, or I guess I should write that as radical 2 over 2 plus ln of, or actually plus 1/2 ln of the absolute value of 1 plus radical 2. And that is my final answer, and that is approximately 1.148, right? So this whole idea of trig substitution can be helpful in application problems such as arc length, or even in those volume area ones. These formulas here, sorry, it's kind of glitching out on me. These formulas here, Theorem 8.2, you can use those for quick stuff like these application problems, but if I specifically ask you for a trig substitution problem and ask you for all the steps to solve it by trig substitution, you must show all the work, right? You can't use those formulas. Thank you.